Let's look at compound events, which means more than one event happening. Before we were looking at just one outcome. For example, I have an urn with marbles in it. There are four of them, two red, one green, and one white. So we're going to make a sample tree to determine the possible outcomes for drawing the marble. Now, notice that I am going to put the marble back. So every time I draw, there will be four marbles to choose from. So that will shape our sample tree. The first time I draw, there are four marbles to choose from, and there are two reds, a green, and a white. Now, normally on a sample tree, I could actually combine these two branches and work with it, but I'm not going to worry about that too much right now. Okay, so I'm going to show both red. One red has maybe a dot on it, one doesn't. And there's your green, and there's your white. Now, since I'm going to put whichever marble I get, if I pull the red, I'm going to put it back, or the green one, or the white one. I'm going to put the marble back. So all four are available again for the next draw. So there's all four for this marble, the second marble, the third, and the fourth. That gives me an outcome. So I'm going to get, if I go up this branch, red, then red, I get red, red. Red, then red, I get red, red. So I'm actually going to get red, red twice. Then this branch is red, green, red, white. So my sample space for these set of four branches, I have red, 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 green, and red, white. I have a total of 16 outcomes. So how many outcomes had a green marble first and then a red marble? Well, there's the green marble I draw first and then the red. Two outcomes, okay? So I have two outcomes here. The question I have then is, what is the probability you draw a green marble on the first draw? So this is the first draw. Out of these four outcomes, the green is one of them, and each of these are equally likely. There's no reason to think that this red marble is more likely than that red one or that green one or that white one. So the probability is 1 out of 4. What is the probability you draw a red marble given that you drew a green marble? Well, it's going to be 1 out of 2 because there's, if I drew the green marble, how many possible outcomes are there for the second draw? So when I do given, I'm not doing the probability of getting a green. I'm doing the probability if I've already gotten a green, what's the probability of getting a red? So 2 of these are red out of 4, so your probability is 1/2. Now, the probability of getting a green then red marble, well, there are two outcomes here. See, there are two greens then reds. That's 2 out of 16 total outcomes, or 1/8. But there's a neat thing I can do. I can actually multiply the probability of 1/4 times the probability of 1/2, and it gives me the same answer. Okay, let's look at the same urn, except this time we're going to not put the marble back. So I have my sample tree here. How does that change it? Well, this red marble is going to be gone. That should disappear. This is the second red marble, so that branch should disappear. The green, I can't draw it again because it's gone. And the white one, I can't draw it again because it's gone. So this gives me this smaller sample space that you see it right. There are only 12 possible outcomes. So how many outcomes had a green marble first and then a red marble second? So let's look at green. You have green, red, green, red. 2 of them. All right, 2 outcomes. Now, what's the probability that he draws a green marble and then a red marble? Well, there are 2 outcomes here out of 12, so the probability of green then red is 2 out of 12, or 1 out of 6. Well, let's take a look at the individual probabilities. The probability he draws a green marble in the first draw, that should be 1/4 because it's 1 out of 4 outcomes. Now, if he draws a green marble, what's the probability he draws a red? Well, there are 3 marbles in the urn. None of them is more likely than the other, so there are just 2 reds and 1 white, so we say that probability is 2/3. Now, notice how you can put these two probabilities together again by multiplying them, and it gives you, that would give you 2 over 12, or 1/6. So you can actually multiply probabilities along these sample trees and tree diagrams, and I would strongly recommend it. So if A and B are independent, then the probability that B does not affect then the probability of B does not affect the probability of A and vice versa. Therefore, the probability of A and B is the same as probability of A. So what am I meaning there? When you notice that when we didn't replace it, the probability of red changed from 1/2 to 2/3, all right? But when we did replace it, it was always 1/2. So basically, if it's independent, it doesn't matter if A happened here, probability of B is the same. And this is also saying the same thing. So events that occur without replacement are usually dependent. So when we saw the urn, we were changing our probabilities. Now, which set of events is dependent here? Well, drawing a marble from an urn and replacing it, that's what we just talked about. That's independent. Rolling a die and drawing a card, the card doesn't know what you did on the die. Drawing 2 marbles from an urn, but without replacing them, that's dependent. Rolling a die twice, die don't care if they repeat or not, it's independent. Rolling a die and flipping a coin, independent. Drawing a card and flipping a coin, independent. Flipping a coin twice, independent. Drawing 2 cards from a deck. Now, if you're doing it and keeping both cards, which you usually do if you're playing a game of cards, then that would be dependent because you've changed how many cards are left for the second draw by your first draw. So anyways, we put all this together and we get the multiplication rule for probability, which is if the events are independent and you're doing A, then B, well, the probability of A and B, getting them in that order, is the probability of A times the probability of B. For dependent events, what has to change is you have to take into account, does A affect the probability of B? And multiply that new probability there, like we did 2/3 instead of 1/2. So let's look at some examples. If we know probabilities, we can use this rule to make predictions without having to count every outcome. The batting averages for some of the Round Rock Express players are here, and this is from a couple of years ago. Are the probabilities of getting hits dependent or independent? Well, assuming they're good players and they try not to let the play of other people affect them, they should be independent. All right. So let's calculate the probability that Carlos Pequero gets a hit and Thomas does not. So the probability would be the probability of Carlos getting a hit times the probability of Thomas not getting a hit. So probability of Carlos getting a hit is 0.667. I have the little complement here because I'm doing Thomas not getting a hit. Now I'm using the 1 minus 0.33. Go ahead and subtract that and multiply these two out, and I get 0.440, or 44%. So that's actually pretty high. Interesting. All right. What's the probability that both batters get a hit when it's Hanser Alberto and Kyle Banks? So we're going to have them both get a hit. Well, it should just be the probability for Hanser times the probability for Kyle, or basically 0.302 here and 0.327. Multiply those out, and I get 0.099, or basically a 10% chance. Now, let's go ahead and look at rolling a die twice. Are the two rolls independent or dependent? And I should say that they are definitely independent, all right? One roll does not affect another. What's the probability of getting a 5 and then an even number? Well, the probability of a 5 is 1/6. Probability of an even number on the second roll is 1/2. So I just multiply those two. 1/6 times 1/2 is 1/12. Now there's a reason I'm not putting the little and symbol in here, and I'm going to explain that in a second. What is the probability of rolling an even number than a 5? All right. Well, the probability of a even number, I should change the order here between these two. An even and then a 5 is 1/2 times 1/6, or 1/12. Then finally, what's the probability of rolling an even and a 5 in any order? So you kind of have to take that into account, because this first one counts and this second one counts as getting an even and a 5. So I would just add these two probabilities and I would get 1/6. So let's go ahead and talk about or probability. So I'm going to revisit the urn with 4 marbles that has 2 red, 1 green, 1 white. And we're going to use the sample tree. All right. So first of all, I'm just going to write the outcomes here because the sample tree doesn't fit so well. And determine the probability you get a green marble on the first or second draw. Well, these are the ones where I get a green marble on the first or second draw. How many, and I'm going to write it down, probability of green or on first or second. That's going to be 7 out of 12 because 7 of these have a green in them somewhere. When I add the probabilities of getting a green on the first, well, that's going to be 1/4. And I add the probability of getting green on the second, that's 1/4 as well. And I add those two together and I get a half. Why aren't I getting the same answer here as I was up here? Well, we're not going to get the same answer because we double counted this guy right here. He's in the answers for the when green is first. There's 1, 2, 3, 4. But he's also part of the group when green is second. So it's double counted. How do we fix that? Well, wherever there's that overlap, we have to subtract the double counts out or the double probabilities. So the or probability rule or the formula, and you'll see this on your math chart, probability for A or B is equal to the probability of A plus the probability of B minus the probability that they occur at the same time, A and B. So how does that work out in our example? Probability of green on the first marble or on the second is equal to the probability of green on the first, which is 1/4. Probability of green on the second marble, also 1/4 because we're putting the marbles back. Minus, is it possible to get green on both the first and the second marble? So that would be this one. Yes, it is. It's right there. 1 outcome out of 12. So we subtract 1/12 and we get 7/12. So now our answer matches what we should have gotten if you just counted the outcomes. All right, we're going to practice one more with an or, and I'm changing this to a roll a die once because I want to keep it straightforward. So what's the probability of getting a number greater than 3 or an even number when we roll a die? So I'm writing down the formula again, and now I'm going to rewrite it with the in context of the problem. Probability of greater than 3 or an even. So that's equal to the probability of a number greater than 3 plus the probability of even minus the probability both of these happen at the same time. So we can talk about that. Well, the probability of getting a 3, greater than a 3, is 3 out of 6 because you can roll a 4, 5, or a 6. How many evens are there? There are 3 out of 6 because there's 2, 4, and 6. Which one of those did I say again for both of those? Well, that was the 4 or the 6, and then the 6. Both of those are not only even, they're also greater than 3. So I double counted them, and I have to subtract out that probability.